This video has the non-welder in mind as I try to provide an overview of the flux-cored arc welding process. I'm trying to provide a basic understanding of some of the more common welding processes in order to help non-welding people understand some of the limitations of these welding processes, as well as providing some basic vocabulary to non-welding people so when they need to deal with welding professionals, everyone is talking the same language. I'd like to acknowledge where I acquired a lot of the information from. The Nuclear Regulatory Commission has an Introduction to Welding Technology and Codes course posted out there on the internet. Pretty much government stuff. It's public domain, so I hit that one pretty hard. Can Teach, public domain, educational and reference library on the Can Do Technology site. It's, Canada's nuclear program, Canada deuterium, uranium reactors. They've got a bunch of stuff. I've left the web pages here. The U.S. Army Training Manual 9-237, Welding Theory and Application. Heck of a lot of information in there. And then the U.S. Navy NavEd TRA 14251 Alpha, U.S. Navy. I'm pretty sure that's the hull technician one. And they've got a couple of chapters in the hull technician training manual that are pretty good. And I've pilfered some information out of there. So that's where the bulk of this material came from. So I've modeled it to fit a format for, instructing non-welding engineers into the basics of, welding and what some of these acronyms are, and trying to let you see what's going on behind the curtain so you can see what's up with the great and powerful Oz. So anyways, this is where most of the information came from. My name is Gary Pace. I'm a professional engineer and a certified weld inspector. I work for Texas Metallum Welding Engineering, which is me. TexasWeldingEngineering.com is my website. There's an email address if you have any questions or want to contact me in regards to welding engineering, or if you have welding questions, give me a shout out. I usually get back to you relatively quick. So the following is a list of factors affecting weld process selection. This is thrown in here, to give you an idea of things that you need to think of when you need to get something welded. Nothing will make a welding person crazier than just saying, just weld it. Well, what criteria do we need to meet? It's like telling somebody, hey, just go to Texas. Well, where in Texas? El Paso, Beaumont, Dallas, Brownsville. Come on, give me a region at least. Give me a little bit closer. So that's what this list here is doing. The type of base metal we're going to weld, the metal thickness, the groove design, the joint alignment, the skill level of the welder, the welding position, the rate of the weld deposit, depth of penetration, impact strength and mechanical properties, corrosion resistance. Welding position is big because, what are we welding? Are we welding on something that's the size of a house, or are we welding on something that's the size of a pizza box? So that's one of the biggies there. The type of base metal and the thicknesses, that's going to help drive what process we're going to use too. If it's something the size of a pizza box, we're probably not going to use submerged arc welding. If it's something the size of a house and we're building a haul truck box or just some massive structure, we're probably going to use stick and flux-core, and we're probably not going to use a lot of gas tungsten arc welding. So these are all considerations that need to be kept in mind when we're selecting a weld process. The flux-cored arc welding process, also known as FCAW, uses a tubular electrode wire filled with flux. The arc established between the electrode wire and the base metal, as in all arc welding processes, provides the heat for welding. There are two variations. One using auxiliary shielding gas from an external source, the other with self-shielding. The core of the tubular electrode contains fluxing, deoxidizing, and at times alloying additions. The molten slag that floats on the liquid weld metal provides physical protection from atmospheric contamination. You can see these two processes in the two diagrams here. We have on the left the gas-shielded flux-core arc welding process, where you're using a flux and the gas to shield the weld metal. And then on the right, you've got the self-shielded flux-core arc welding. The self-shielded flux-core arc welding is pretty much, and I'm overgeneralizing here, it's the shielded metal arc welding process, stick welding, turned inside out to achieve greater productivity. So you don't have to stop every few inches and change out your electrode. With this process, you can just make a pass and go, and then come back and chip off the slag and do it over again. Flux-cored arc welding. Flux-cored arc welding was developed in the early 1950s as an adaptation to shielded metal arc welding to overcome limitation imposed by the use of stick electrodes. Constantly having to stop and change electrodes. Burn down to 3 or 4 inches, throw that one away, chip everything off and go. Whereas flux-core arc welding, if you're welding on something and you've got a joint that's 10 feet long, you can do the whole 10 feet before you got to come back and clean up. This is a huge savings in labor. It increases your deposition rates, I don't know, exponentially. I was going to use exponentially as a word, but I don't think it's exponentially, but it greatly increases your deposition rate. There's two versions. There's the self-shielded flux core. There's only fluxes that generate the shielding gas. And then you've got the gas shielded flux core arc welding, also known as dual shield. So you can weld steels with this, but it uses a shielding gas like GMAW, and there's a flux on the inside of the wire. So there's a zillion different kinds of dual shield, they call them. I think dual shield's a trademark name, but if you start talking to people and say, hey, I need a flux core that's dual shielded, they'll know what you mean. The people selling the wire, the welding wire, they're going to know what you mean, that you need a flux-cored wire that also needs a gas. And there's a lot of these wires that can go both ways. So, but there are two different versions of flux-cored arc welding. In this slide, you can see a bigger sketch of the self-shielded flux-core arc welding process. In this drawing, you can see where there's the decomposition of the flux that is contained inside the tubular wire. It's getting cooked down in the arc, and it's giving off a shielding composed of vaporized and slag forming compounds, and this protects the liquid weld pool from oxygen and nitrogen, which would cause all kinds of deleterious effects on our solidified weld metal if it went that direction. This sketch is from a military manual, but it shows the gas shielded flux core arc welding process. You can see the difference here is there's an additional component, which is the gas nozzle. The gas nozzle helps bring gas shielding to the weld pool, and it keeps the oxygen and nitrogen out of the weld pool. You've also got the flux in the interior of the flux cord wire or electrode, and it's burning off and also providing a slag covering that's helping to shield the molten weld metal as we're depositing weld metal into our weld joint. So that's the main difference. One has an additional gas shielding component to it. The self-shielded flux core process doesn't. As you can see here, this sketch shows the two main variants of the Flux-cored arc welding. This is from Linnert Welding Metallurgy, AWS 1994, kind of a Bible type book for a lot of welding engineers. There are two basic process variants here, as you can see. You've got the self-shielded, which is on the left side, and you've got the gas shield, the dual shielded, on the right side. The difference in the two is the different fluxing agents in the consumables, which provide different benefits to the user. Usually the self-shielded Flux-cored is used outdoor conditions where the wind would blow away a shielding gas. That's one of the things you have to worry about with gas metal arc welding also is, the shielding gas being blown away. The flux in a gas shielded Flux-cored provides for deoxidization of the weld pool, and to a smaller degree than in the self-shielded Flux-cored, provides a secondary shielding from the atmosphere. The flux is designed to support the weld pool for out-of-position welds. This variation of the process is used for increasing productivity for out-of-position welds and for deeper penetration. Also on this drawing you can see examples of the cross-section of the Flux-cored arc welding electrodes. Various different ways they pinch that off when they're doing the old roll your own cigarette type situation. So it's just a flux. Like I said, it's a flux on the inside of a metal tube. Shielded metal arc welding, same flux, not exactly the same, but same flux outside of a metal wire. They just glue the flux on the outside. This, you put it on the inside. But with the Flux-cored arc welding, you get a better deposition rate because you're not always having to change electrodes. You're in a semi-automatic situation where you're feeding the wire, your electrodes coming off a spool, so you can pull a trigger and just go like the dickens. In this sketch, we can see a typical arrangement of a self-shielded Flux-cored arc welding gun. A couple of items to note on this slide are the fact that there is no mechanism for the delivery of a shielding gas to the weld puddle, as there is no shielding gas needed. The second item of note is the protective hand shield. This is to protect the welder's hand from the thermal energy that is being kicked off from the weld pool. Generally, the self-shielded Flux-cored arc welding electrodes are in sizes larger than those of the gas-shielded Flux-cored arc welding process, and thus run at higher amperages and voltages. This means that there is more heat going into the glove of the welder, hence you need to shield his hand to protect it from damage and injury. So that's the reason you've got the protective hand shield on this gun, higher amperages and voltages. Factors that affect electrode selection. Type of base metal. You absolutely have to know what the base metal is before you start welding on it. Nothing will create bigger problems down the road than not having a positive identification of the base metal. This also can drive welders and welding engineer type people absolutely insane. If you come up to them and say, hey, just weld this, and the welding engineer asks the person who needs it just welded, what is this? And the person needing it welded says, I don't know, just weld it. No, it doesn't work. You need to know what the base metal is before you start, or have a general idea. You might not need certified material test reports, but it's a good idea to know what you're welding on. The metal thickness is another good idea to have, because shielded metal arc welding, there's different electrodes that perform differently on different thicknesses of material. So some are better for sheet metal, some are better for heavy sections of material. Material thickness. Groove design, what's the groove going to look like? What are we trying to accomplish here? The joint alignment, another one. What are we trying to get accomplished here? Available welding current. How big a power supply do we have? How big a welding electrode can we use? Is this going to be a 4-inch thick weld and we're going to do it on a flat position and just be able to pour the coals to it? Or is it something where we've got really small power supply and we're going to have to chunk along at a slower rate. So available weld current is another factor that's going to affect electrode selection. Skill level of the welder is also going to affect electrode selection. Not everybody can weld with every type of filler material, so you need to know who you've got working for you and who's going to be doing the welding. Some more factors that affect electrode selection. Welding position. Not all welding electrodes are designed for all positions. So if you're doing an overhead weld, you're not going to be able to utilize a welding electrode that only runs in the flat position. So you're going to need to determine what your position is, and then is this electrode suitable for that position. The rate of weld deposit. Do we want something that's really going to have a high deposition rate? What are we looking for? Once again, the position is going to dictate the rate of the weld deposit. You're going to be able to put weld metal in faster in the flat position than you will in the overhead or the uphill or downhill position. Depth of penetration. What kind of material are we welding on? Is it a sheet metal weld? Well, a lot of times on a sheet metal weld, you might not want something that's really going to have a lot of penetration. Weld bead finish. This is, how smooth is the weld bead going to be? What are we looking for? Impact strength definitely comes into play, especially in industries such as oil and gas or mining, and especially in locations where the environment's going to play a role and you're going to have very cold temperatures. A lot of steels don't react well to really cold temperatures. Well, most don't. It just depends on what the material is. So impact strength. You need to see how much impact energy this material can absorb before it breaks. Corrosion resistance. If you've got a corrosion, let's say you're making a weld on some corrosion resistant steels, you probably want a weld material that's going to match up with the corrosion resistance of the base metal. So, or you're not going to want a situation where you put in a filter. On this slide, you can see the manufacturing process of cored welding electrodes, and the method of manufacture the same. This is patent number US 780794-8B2. The process starts with a flat strip and then a flux is added, much like sprinkling tobacco on a zigzag paper and rolling your own cigarette. The strip and the flux go through a forming die, which pinches the flat ribbon down into a steel tube containing the flux. The steel tube with the flux is then drawn through a number of forming and drawing dies to produce the desired electrode diameter. The sheath or steel portion of the flux-cored wire comprises 75 to 90% of the weight of the electrode, and the core material represents 10 to 25% of the weight of the electrode. For a covered electrode, shielded metal arc welding, the steel represents only 75% of the weight, and the flux is 25% of the weight. More flux is used on a covered electrode, shielded metal arc welding, than in a flux-cored wire to do the same job. This is because the covered electrode, shielded metal arc welding, contains binders to keep the coating intact and also agents that allow the coating to be extruded. The flux-cored arc welding process is made possible by the design of the electrode with a flux contained in the drawn metal tube. Basically, this is shielded metal arc welding inside out and coiled on a spool. This inside out electrode consists of a metal sheath surrounding a core of fluxing and alloying compounds. The compounds contained in the electrode perform essentially the same functions as the coating on a shielded metal arc welding covered electrode, i.e. deoxidizers, slag formers, arc stabilizers, and alloying elements. When molten metal is exposed to air, it absorbs oxygen and nitrogen and becomes brittle or is otherwise adversely affected. A slag cover is needed to protect the molten or solidifying weld metal from the atmosphere. This cover can be obtained from the electrode coating. Slag is not a part of the final weld and thus does not contribute to the strength or protection of the metal after the welding process is complete. Slag is a waste material and needs to be removed. Removal of the slag is necessary for 4 reasons: visual and NDE inspection of the weld area, aesthetics or visual appearance, if a second layer or pass of welding is to be made on top of the first, to provide a clean surface for coatings such as paint or oil. Removal is usually done using manual or power tools. Manual tools may include a welding or chipping hammer, which has a pointed tip at one end to break up large chunks of slag efficiently, or wire brushes and files. Power tools can include angle grinders with grinder discs, or wire brush wheels, or even pneumatic chipping guns. Many times a file is used to clean up the toe of the weld. The major advantages of flux-cored arc welding are reduced cost and higher deposition rates than shielded metal arc welding. Flux-cored arc welding can also be used in outdoor situations that might not be ideal for gas metal arc welding. Flux-cored arc welding is ideal where bead appearance is important and no machining of the weld is required. Flux-cored arc welding without carbon dioxide shielding can be used for most mild steel construction applications. The resulting welds have higher strength but less ductility than those for which carbon dioxide shielding is used. There is less porosity and greater penetration of the weld with carbon dioxide shielding. The flux-cored process has increased tolerances for dirt and scale. There is less weld spatter than solid wire MIG welding. It is also a higher deposition rate process, and faster travel speeds are often used. Using small diameter electrode wires, welding can be done in all positions. Some flux-cored wires do not need an external power supply of shielding gas, which simplifies the equipment. The electrode wire is fed continuously, so there is very little time spent on changing electrodes. A higher percentage of the filler metal is deposited when compared to shielded metal arc welding, as there are no stubs. Finally, better penetration is obtained than from shielded metal arc welding. Flux-cored arc welding limitations. The slag must be removed. There's a lot more smoke than gas metal arc welding and submerged arc welding. A lot more spatter. Flux-core wire is more expensive. Instead of just making wire, like I said, it's a kind of a roll your own cigarette kind of deal where you start with a flat ribbon of metal and then you sprinkle a powder in it and then you got to roll the powder over, roll that into a tube and then you kink it down into the various sizes. So the manufacturing process is more expensive than it would be for gas metal arc welding. The equipment is more expensive and complex than for shielded metal arc welding too. Shielded metal arc welding, you need some cables, you need a power supply, and you can go. Here, you're going to need wire feeders, you're going to need guns, you can run in, depending on what size of guns you're using, you might need water-cooled guns. It just depends on what you've got going, but it's definitely more expensive than shielded metal arc welding. In summary, flux-core arc welding is an arc welding process in which the heat for welding is developed between a continuously fed consumable tubular metal electrode wire and the workpiece. As the metal electrode melts in the welding arc, it becomes the filler metal for the weld deposit. The decomposition of the flux that is contained within the tubular electrode provides protection from atmospheric contamination. The protection is achieved by gases derived from the breakdown of the flux in the electric arc. Supplemental shielding gas is usually used to give better protection to the metal in the weld puddle. The two different methods are identified by self-explanatory names: flux-cored arc welding with self-shielding, this means without supplemental shielding gas, and flux-cored arc welding with auxiliary gas shielding, with supplemental gas shielding. Flux-core arc welding without gas compares somewhat with shielded metal arc welding in that it can tolerate worse working conditions than a process that requires auxiliary gas shielding. It is less cumbersome because of the absence of gas containers, and it can tolerate drafty conditions. Both types of FCAW enjoy great popularity in the steel fabrication business. The FCAW process has two major advantages of very high deposition rates and the metallurgical benefits of a flux. To increase production, powdered metals and sometimes alloying elements are added to the flux material in the core of the wire tube. The process can be used in all positions, although the larger wires and higher amperage levels can only be applied in the flat and horizontal positions. The equipment is essentially the same for externally shielded flux-core arc welding as is required for the gas metal arc welding process. For self-shielded flux-core arc welding equipment is the same, except that no bottles, lines, switches, or nozzles are required to provide a shielding gas. When I give this presentation live, this is the point where I usually ask if anybody's got any questions, but seeing as how this is a presentation that's on the internet, you don't get that. So if you've got any questions, send me an email. If you have any need for a welding engineer, same contact information. My website is texasweldingengineering.com. My name is Gary Pace. Occasionally I get a question in regards to where I went to school or where I got my welding engineering degree. I went to Montana Tech in Butte, Montana. It's a 4-year ABET accredited welding engineering school, small class sizes, good faculty, good value for your money. If you're interested in welding engineering and you want to check out the state of Montana, Montana Tech's a good place to visit. Go to school.